got some agreement. How many of you agree with A, B, C, and D? How many of you got a different answer? Lucci, what'd you get?
A, C, B, D.
And different? Ian?
A, B, D.
Okay, so as we go through these different answers, I want to talk about some reasoning behind these answers. So, first of all, let's talk about A, B, C, and D. Let me have Jack explain to me what your reasoning was behind your ranking.
One, I thought that the two that had the highest, like, that were the furthest from the ground, had the most gravitational potential energy.
Okay.
So I thought that they would go the fastest. And then because C's slope was more than D's, I thought it would go faster, even though it's a little bit lower, but it's not that much lower.
Okay. So first you thought the ones that are highest above the ground need to be faster. And then when you look at C and D, you looked at the slope to rank the last two. So these two are based on height, vertical height, right? V height. These two are based on angle. Why didn't you use height for C and D or angle for A and B?
Well, I feel like I sort of used both for A and B because they're both still 28 and 22, which is
Still pretty high.
Still pretty high.
So you took both into consideration, basically.
Yeah.
Okay. You took both of them into consideration. And weighing the two, 28 obviously was the highest, and that was kind of consistent across the board. B was high, but it also had a high angle. And then between C and D, the angles were different, but the height was kind of interchangeable. One had a low height with a high angle and a low angle with a high height. So let me go with A, C, B, and D. That one was Lucci. What was your reasoning?
I don't really know.
A was 28, 22, 22, and 18.
Oh.
So,
Because B and C are like the same. But,
okay.
C is 10 meters and B is 15, so I thought if it's lower, I thought that's where like it cuts off and that's where it starts going flat.
Okay.
I don't know if that's right.
Right here is where it starts going flat?
Or at the 10 meters, so I thought it had more like time to actually speed up. I think I looked at it.
Okay, so this one was more an errand analysis.
Yeah.
So you want to change your answer?
Yeah.
Okay. Did you want to change it to Jack's or did you want to change it differently?
Jack's.
Okay. So let's go to A, B, D, and C. Ian, what was your reasoning behind this one?
Basically the same, except that E being higher, whatever comes to the lower.
So your focus here was height. I saw some students with some diagrams. I loved seeing the diagrams. So anyone want to volunteer a diagram that helped them analyze this? I saw one for Daisy in the spot. What did you draw?
I just drew an LOL chart.
An LOL chart. Oh my gosh, that's like extra credit in my heart. An LOL chart. All right, so let's do an LOL chart. We've got the ball. We've got the ramp. We've got Earth. And what is my initial energy type? Gravitational, GPE. What's my final energy type? Kinetic energy. And do I have any other energy types here? No. Okay, so gravitational potential energy, the definition is related to change in height or height above the ground. The definition of kinetic energy is speed. or motion. So it doesn't mention anything about the steepness of the angle, right? Nothing about the steepness of the angle. So the correct answer for this one would be A, B, D, and C. The height is the only factor that influences the amount of speed or the amount of kinetic energy at the bottom, and the angle has nothing to do with it, surprisingly. And the reason why, Ian,
The angle does extend that way, change the acceleration.
so the angle will change its acceleration, but here's the deal. If we have a 10 meter, if we have, let me see if I can compare. Okay, here and here. They're both 22 degrees, right? But the fact that the 15 is starting much higher, it has more time to increase in speed. Here, this one might be steeper, it has less time to increase in speed, so even though it'll accelerate faster, it has less time to accelerate. They kind of counterbalance each other.
But then for A and B, if you said the angle doesn't matter, then like, why did we choose A first if like we're only looking at the height?
So A is the highest, right?
But they're A and B are both.
Oh,
the
A
same.
and B. So in this scenario, you would actually get A and B to be equal.
Oh really? Like it
You
actually.
can interchange them because they would be equal, and then D and C would be consecutively less and less. Was that the same question I had over here? Yeah. So the height is the most important. The angle will allow you to speed up faster, but you have a shorter amount of time to do it. Any questions? All right, physics students. So in this demonstration, if you were absent and watched my video, this is the data that we collected together for the compression distance last class, and we were able to get the slope of 187 newtons per meter. Now, in class today, I had all the students put up their spring constant values, and we got an average spring constant. It was pretty consistent throughout all my classes. I got 181 and 183 alternately. So our spring constant, we can just say, is 183 for our average value. It's very close to 187, and since it's such a big number, these few digits aren't going to make a huge difference. But we want to reduce our error as much as possible. So we're going to use the 183, the class average, which the more data you take, the more accurate it's going to be. And then we're going to calculate the elastic potential energy. So this is something you're going to do at home. Your elastic potential energy, EPE, one of the equations is 1/2 K delta X squared. And we're using this equation instead of the 1/2 force times delta X equation because we have this delta X. So you're going to use 183, plug it in for your K value, and then you're going to use your delta X and square it, which is the delta X that we got last class for number 1, the delta X for number 2, and the delta X for number 3. When you do this calculation for 1, 2, and 3, you're going to plug it in here. And once you plug it in there, if you look at part 3, you also have an elastic potential energy in your next chart. So you're transferring this information over. So I'm just going to slide this down. We already did this LOL chart. I want you to, once you've calculated your energy is the same amount of energy transferred each time. Based on your calculations with this equation, what do you think? We didn't do a graph, but you can analyze it numerically. And then the very last part, you're going to do first, I know it's hard to see. You're going to do this LOL chart, LOL chart. We're going to talk about it in the video, so I want you to do it first, and then you can check your answer with the video. And then you're going to take whatever information you got from equation 1, whatever values you got from the part 2 data table for elastic potential energy, you're going to copy all that information down in the chart for part 3. So all of this is just going to be copied from part 2. Now, I'm not going to have you calculate the distance, and I'm not going to have you calculate the height. I will walk you through the process of what we did, but I'm just going to give you the values because we don't have a nice Pasco capstone graph to do this analysis. It's more just using a ruler. So I'll give you these number of values, and you can do your analysis with them next class. So first of all, I am going to talk you through this diagram right here. So in this diagram, it walks you through exactly what we did to get our change in height. In your data table, it's going to ask you for a distance, and it's going to ask you for an initial height, and then a change in height. The only real data we need is the change in height, and we're using the distance and the initial height to get there. So what you are going to record in your data table, since you're not here to collect the data, is just the change in height, but I want to show you exactly what we're looking for. So first of all, what my students did was they took a slow-mo video camera to find this distance that the cart traveled. When they found that distance, they were able to determine what the final height would be at that distance point at the top. Now, right here, our cart is not at 0. So we need to make sure that we don't include this initial height because it's only supposed to be the change in height of the cart, and we're looking at this end of our cart as our reference point. So we want to know how high did our cart move from the back end to the back end. So by taking this initial height, and they found the final height using a slow motion video, the important data they got out of this was the change in height. The change in height that the cart went from initial position to final position. This distance doesn't really matter. It's just a reference point for us to find our final height. So this is the data that I'm going to be giving you. Okay, so we've got our cart, we've got our elastic kind of launcher, and our cart starts at position 1. Then we're going to go to position 2, and then we're going to go to position 3. So for each of these launches, if I start at position 1, it is a small compression distance, meaning a much smaller elastic potential energy. When I launch it, I'm going to take this initial height right here, and I'm going to subtract it from its final height up here. So you can see, and I'm going to use a pretty frictionless flat surface to trigger my launch. It's a pretty small height difference, right? It goes from here, maybe up a couple inches, and back down. Now let's do it for number 2. So you want to go from the bottom of the cart to the bottom of the cart. So if my reference point is at the bottom, I want to make sure to find out where on my ruler, because I do have a ruler on this ramp, it is going to reach its maximum position. Students use slow motion cameras. I'm eyeballing it. So if I started down here, that's my initial height. I am going to launch it and see where the bottom reached somewhere right here at 87. So I'm going to measure the height at 87, and from here to here, if I subtract those two height differences, I get my change in height. Notice how much further it goes at 2, and just to see, it goes even higher. It went all the way up to 57 here. So a much greater height difference at that point. So stay tuned. I will give you the data for that for you to record, and then we will do the rest of our data analysis in this class. Okay, so the data that we collected for the height change, again, the distance and initial height, the students needed it to do it in class, but the most important part of this data is the change in height. So we got 0.009 meters, 0.0584 meters. This is using our most accurate data. And 0.0957 meters. So this is the change in height that you're going to use. Again, your elastic potential energy comes from data from part 2. And then next class, we're going to do an analysis of the elastic potential energy versus the change in height. And hopefully we can get one of our physics helper equations out of doing this analysis. So after this, I am going to go over the LOL chart for part 3. Make sure you do it on your own first, and then you can go through the answers when you're ready to, when you've finished it and you're ready to check your answer. The initial scenario is at the very bottom of the ramp. You have your cart fully compressed, no motion yet. What type of energy would you call this scenario? First, my system. I'm just going to throw everything in there. Earth, cart, and the spring, and the ramp. So what's my initial energy for my first L? What do I have here? What type of energy? When it is fully compressed, not yet moving at the bottom of the ramp. Let me have Frankie.
Elastic potential.
I've got elastic potential energy. I'm going to throw in 2 boxes. It doesn't matter how many as long as you keep it consistent. All right, let's look at the second scenario. Just as it is released, it no longer has any compression in the spring, and it is released from the ramp. It is right at the point of it being launched. Take
I said 2 kinetic, 2 gravity.
2 kinetic and 2 gravity. So
Oh, I didn't realize you had 2. So
That's
it's
okay.
one of each.
So you could say kinetic energy and gravitational potential energy. So it's increased a little bit of position and it has some motion. Did you have something different, Mike? Another way I did it, because I assumed, kind of like just as it leaves the ground, we can assume that gravitational is negligible. So for me, I would look at it as maximum kinetic energy, negligible gravity. So you can also do it like this. 2 kinetic, no gravitational. Either one is justifiable, right? Last but not least, at the very top of the ramp, in the moment where it is transitioning forward to backward motion, what type of energy do I have there, Danny? All gravitational. It is above the ground. It's hit its highest point, and it would be gravitational potential energy. So this is your LOL chart analysis. You start with elastic. It transitions to kinetic, maybe a little gravitational, and then it increases to all gravitational. Energy transfer. Are there any questions on this? Pull out your notes with all the energy types on it. It's this yellow sheet in your chart. You've got kinetic energy. You've got gravitational. And you've got elastic. I want you to write down the equations. They're all in your physics helper, but it's always good to have it in a nice place. Elastic is 1/2 force times delta x and 1/2 k times delta x squared. This we already learned from our spring lab. You have a gravitational equation, which is mass times gravity times height. Gravity is 9.8, and height is the change in height, like what we did in our class, what you calculated in your data. And then kinetic energy is very similar to elastic, except it's based on 1/2 mass times velocity squared. So they look the same. They have the same basic structure. We're going to prove this next class, and then maybe prove this on Tuesday. If we don't have time, I'll do it on Thursday. But these are the equations that I want you to know. Look at your physics helper. Make sure you know where to find them. And the homework tonight is going to be based on your reading from last night, these equations, and then you also want to prepare for your quiz on Tuesday. It's going to be on worksheet 2. So all of those notes that we took on spring forces, the post lab that we did, area under the curve, I want to make sure that you guys understand how to do that for Tuesday's quiz.